Assalamualaikum. Hi. This is the continuation of the Bioreactor Engineering Part 1. And this slide presentation will be on the modeling growth kinetic. You can refer to textbook written by Schuler and Cargie, the Bioprocess Engineering Basic Concept, 2nd edition by Prentice Hall. Can read in chapter 6. Okay, class. The cellular composition and biosynthetic capabilities change in response to the new growth condition, which is known as unbalanced growth. The constant cellular composition and balanced growth predominates only in exponential growth phase. If the decelerating growth phase is due to substrate depletion, meaning that less of substrate in the medium, rather than due to production inhibition, then the growth rate will decreases with respect to decreasing of substrate concentration. Complete description of growth kinetics of a culture would involve recognition of the structured nature of each cell and the segregation of the culture into individuals, unit, or cells that may differ from each other. We have two different models, which are, the first one is structured models, the other one is unstructured models. The structured models is a model which divides cell mass into components by molecule or by element and predicts how these components change as a result of growth. So these models are very complex and not very used often. The next one is unstructured model. So this model assumes balanced growth where cell components do not change with time, much less complex and much more commonly used. The valid for batch growth during exponential growth stage and also for continuous cell culture during a steady state operation. So mostly used is these unstructured models. As being mentioned before in the previous lecture, the main equation used in the growth kinetic is the Monod equation. You have to remember this Monod equation, okay, and all the variables, parameters involved in the Monod equation. Especially, you need to know how to get the mu max or mu m, the maximum specific cell growth rate, from the graph of x versus t or ln x versus t. And also how to get the Ks value from the graph of mu versus s. This is the batch culture growth model. Okay. As been mentioned in the lecture before, this equation mu equals to 1 over x dx dt, which is equivalent to the Monod equation mu m s over ks plus s. Okay, this is very important equation. Okay. Then, if there is a changes in s to changes in x through y-axis, okay, so from the equation of x minus x naught equals to y xs times s naught minus s, you rearrange, so it becomes s equals to s naught plus x naught over y xs minus x over y xs. Okay, then substitute in the equation in s. Later you will get the below equation here. Dx over dt equals to mu m x s naught y xs plus s naught minus s over Ks yxs plus s naught yxs plus s x naught minus x times x. Okay, where t is at 0 and x is equivalent at x naught. Okay, so the equation for yxs, okay, here x minus x naught equals to yxs times x s naught minus s. Okay, if you use this equation, you may able to find the yield coefficient of cell concentration over substrate, which is it will become yxs equals to s naught initial value of substrate minus the final value of substrate over x the concentration of cell minus x naught the initial concentration of cell. So by using the equation, you may able to determine the yield coefficient of cell concentration over substrate. Then, by rearranging the previous equation dx dt after substitution of s value of equation, then you will get this equation known as logistic equation. Now you have to integrate the previous equation, okay? Then you will get this equation. Alright. So this equation, the logistic equation, it describes the sigmoidal shape growth curve. So the value of x, okay, asymptotically it reached to the value of y xs s naught plus x naught. Okay, so the plot that corresponds to the rate expression where we have x infinite here is the maximum cell mass, which is also known as a carrying capacity. Usually this logistic equation is being used in order to predict any variable value, okay, any variable parameters related to the fermentation, okay, such as what is the final of cell concentration that we will get, what is the final substrate concentration, okay, and what is the yield of cell over substrate. Okay, so we can use this logistic equation. Though the logistic equation qualitatively predicts the shape of batch growth, however, it is not very useful in order for you to determine the Ks and mu max value. Okay, then what you have to do is you have to plot a graph of mu versus s, like the one below here, okay, in order for you to determine the Ks value, right? And in order to determine the mu max value, you have to plot a graph of ln x over t or graph x over t. Okay, here it shows the graph of x, ln x over x naught versus t. It also can be used, but normally we used graph x over t or ln x over t. Okay. Please do problem 6.1, okay, in the textbook, in the Schuler and Cargi textbook. Then you will have the idea how to identify the mu max and the Ks value by using the data given in the problem. In the production from the fermentation, we might be able to identify the productivity of the fermentation. So what is the productivity? Productivity, Okay, it is being identified for cell mass or growth associated product. Okay, then in the fermentation, usually we are using the batch fermentation. Okay, so it is also known as a batch culture. We will assume that Kd is equals to 0 because of we're talking about the growth associated product, which is referring to the product produced at the exponential phase where the Kd is equivalent to 0. There is no death rate. Okay, and the Qp is equals to 0. The rate of product formation at the beginning is equals to 0. Okay, the product is started to produce as the cell is growing. Okay, so here you can see RB is denotation of rate of cell mass production in batch culture. Okay, in one batch cycle, and you can determine this RB, okay, by using the equation of XM minus X over TC, which is also equivalent to Y maximum of cell concentration over substrate, Gill coefficient, times S naught over TC. Okay, so TC is a batch cycle time, where it can be determined from 1 over mu max times ln xm over x naught plus TL. TL is the lag time for harvesting and preparation. Okay, so from the equation here, I would like you to identify all those terms in this equation. What is SM, what is S naught, what is X. Okay, in order for you to understand more on the equation. The total amount of cell mass produced, okay, you can identify it from the equation of xm minus x naught equals to yxs times s naught. Okay, and the rate of cell mass production in one batch culture, which is denoted by RB, is given by the equation 3 here. Alright. Okay, then after you substitute, if you can see here, is xm minus x, to substitute the value, the equation, okay, yxs s naught. That's why you get this equation number 3. Okay, and then where TL is the sum of times required for the lag phase, harvesting and preparation, and if the volume of the bioreactor is given, then the productivity you can determine by using equation 4 here. VR is the volume of the reactor during the reaction. It's not the volume that can be occupied by in the reactor, but it's the volume that being used during the reaction. Okay, it's a working volume.